Hey folks, how you doing? Let's go ahead and get started. Um, we're going to be working on the AES field today and a function called xtime, which will help us do calculations in that field. Just as a reminder, exam 2 is uh, is not this Saturday, but it's the following Saturday. So it's Saturday, March the 20th. If you need to take the exam a day before or a day after this, let me know soon so that we can make accommodations. But the structure should be similar to the last exam. We'll have a window of time to complete the exam and submit it. All right. So let's go ahead and move on. So this is a problem we did last time. I just want to review how this works. We have this field with this modulus. This polynomial is the polynomial x to the fourth plus x plus 1. And as a result of this being a fourth degree polynomial, let's call this polynomial p of x. Since p of x is fourth degree, the only values that are in this field have degree 3 or less. All polynomials in Z2x mod p of x have degree 3 or less. So this polynomial has degree or less, and so does this polynomial, so that's okay. But then when I multiply them together, we run into a problem because this is going to be x to the fifth plus x cubed plus x squared plus x cubed plus x plus 1. The x cubes cancel, and we're left with x to the fifth plus x cubed plus, x squared plus x plus 1. And so how do we get rid of this x to the fifth term? We take the remainder when we divide by this polynomial. So what we're going to do is we're going to compute x to the fourth plus x plus 1 into the polynomial x to the fifth plus x squared plus x plus 1. To get x to the fourth into x to the fifth, we have to multiply by x. And so we get x to the fourth plus x squared plus x. And then, x to the fifth plus x squared plus x. And then all of these terms cancel, and we have a remainder of 1. And so this is congruent to 1. It is not it's not x to the fifth. It's 1 inside this field because we need a polynomial of degree 3 or less. That means that these two functions are inverses of each other inside this field as well. So AES works like this, but the field is modulo a much larger polynomial. This is an 8th degree polynomial, and that means that all elements in this field have degree 7 or less. That means that they can be stored in an 8-bit byte, because remember, the first term is 1, which is x to the 0, and then we have x squared, x cubed, up through x to the 7th. So we've chosen, I say we, but Phipps chose this polynomial here in order that the elements will be storable inside an 8-bit byte. And that means that any product that results in a polynomial of degree 8 or higher, we have to reduce this by multiples of p of x. And that can get kind of complicated. It might take several steps. Let's just try multiplying these two polynomials together. In hex, we would write this as f0 times 80. If you want to think about this as hex instead of binary. But this is the polynomial x to the 7th plus x to the 6th plus x to the 5th plus x to the 4th multiplied by x to the 4th. And that part's easy. That's x to the 11th. I'm sorry, not x to the 4th, x to the 7th. So we get x to the 14th plus x to the 13th plus x to the 12th plus x to the 11th. Well, this is the wrong degree, so we have to divide x to the 8th plus x to the 4th plus x cubed plus x plus 1 into x to the 14th plus x to the 13th plus x to the 12th plus x to the 11th. So where did this polynomial come from? This is this polynomial right here. And this is a constant polynomial in the AES field. This is the field that polynomial we use to reduce large answers that are overflow 1 byte. Well, x to the 8th goes into x to the 14th, x to the 6th times, and then we get x to the 14th, and then x to the 4th times x to the 6th is x to the 10th, then x cubed times x to the 16th is x to the 9th, x plus x to the 6 times x to the 6th is x to the 7th, and then 1 times x to the 6th is x to the 6th. And so I got rid of the x to the 14th, but I still have to get rid of x to the 13th now. This step is going to be a little bit weird here because we're subtracting, and so you'd think I should get minus x to the 10th. But in binary, minus 1 and positive 1 are the same value. So I can write this as plus x to the 10th, plus x to the 9th, plus x to the 7th, plus x to the 6th. And now I have to divide x to the 8th into x to the 13th. Well, that goes in x to the 5th times. And so x to the 13th, x to the 4th times x to the 5th is x to the 9th. X cubed times x to the 5th is x to the 8th. X times x to the 5th is x to the 6th. 1 times x to the 5th is x to the 5th. And the x to the 13ths cancel. But I'm left with x to the 12th plus x to the 11th plus x to the 10th. The x to the 9ths cancel. X to the 8th, x to the 7th, x to the 6th cancels, and x to the 5th. So I have to divide again. X to the 8th goes into x to the 12th 4 times. And then we have x to the 12th. X to the 4th times x to the 4th is x to the 8th. X cubed times x to the 4th is x to the 7th. X times x to the 4th is x to the 5th. And 1 times x to the 4th is x to the 4th. And so we'll get some cancellation here. These cancel, these cancel, these cancel, these cancel. But we still have x to the 11th plus x to the 10th plus x to the 4th. X to the 11th is still too big, so we have to take x to the 8th into x to the 11th, and we get x cubed. X to the 8th times x cubed is x to the 11th. X to the 4th times x cubed is x to the 7th. X cubed times x cubed is x to the 6th. X times x cubed is x to the 4th. And 1 times x cubed is x cubed. And so now we have those cancel. We're left with x to the 10th, x to the 7th, x to the 6th, and x cubed. And x to the 10th is still too big. So we take x to the 8th into x to the 10th. That goes in x squared times. And we get x to the 10th. X to the 4th times x squared is x cubed. X times x squared, or x to the 6th, sorry. X times x squared. X cubed times x squared is x to the 5th. X times x squared is x cubed, and 1 times x squared is x squared. We subtract I'm running out of room down here, but what we're left with is x to the 7th plus x to the 5th plus x squared. The x to the 10ths cancel, the x to the 6s cancel, the x to the 3rds cancel. And this finally is small enough that it fits. X to the 7th, x to the 5th, 4th, 3rd, x squared, x to the 1st, x to the 0. And so this is our result. But we had to divide 1, 2, 3, 4, 5 times to get this down to the right degree. Okay? So in general, multiplication can be very complicated in this field. But multiplying by x, which is the polynomial x plus 0 for the constant, so that's 1, 0, is always pretty easy. So let's try multiplying this polynomial by 1, 0. So this is x to the 7th plus x to the 6th plus x to the 4th plus x plus 1. And we're going to multiply it by x. And that's going to get us x to the 8th plus x to the 7th plus x to the 5th plus x squared plus x. And then we're going to have to divide that polynomial by x to the 8th plus x to the 4th plus x cubed plus x plus 1. That's going to go in one time, and we have x to the 8th plus x to the 4th plus x cubed plus x plus 1. The x to the 8ths cancel and the x's cancel, and we're left with x to the 7th plus x to the 5th plus x to the 4th plus x to the 3rd plus x squared plus 1. And we're done in one step. We got the answer. 1, 0, 1, 1, 1, 1, 0, 1. But I want to show you a couple of things here. This is the polynomial 1, 1, 0, 1, 0, 0, 1, 1. If we're multiplying by x, everything just shifts over a power. This is 1, 1, 0, 1, 0, 0, 1, 1, 0. And so this step is just a left shift. We're shifting everything over by 1. Well, that means that this power can't go any higher than 8. This could go from x to the 7th to x to the 8th, but we can't end up with a 9th, 10th, 11th, 12th, any higher degree polynomial, which means that if we're dividing by x to the 8th, this is always going to be 1, assuming we have to divide it all. And then this is just going to be subtracting 1 times this. So this is going to be, I want to write this out in bits here. This is 1, 1, 0, 1, 0, 0, 1, 1, 0. That's what we got here. We're going to subtract x to the 8th plus x to the 4th plus x cubed plus x plus 1. This is our AES polynomial. But in Zmod 2, subtracting and adding are the same, and so this is just an XOR operation, and we get 0, 1, 0, 1, 1, 1, 1, 0, 1, which is exactly the same answer we got up here. And so this is just an XOR. And so while in general, multiplication in this field is tricky to do in code. Multiplying by 1, 0, which is the polynomial x, consists of three parts. We do a left shift, then we check to see if we have an 8th power. That won't happen if this is a 0. I'm sorry, if this is a 0, because then even with a left shift, we still won't have an 8th power. If we don't have an 8th power, then we're good. We can just return the answer we have. But if we do have an 8th power, then we finish up with an XOR step right here. Okay? So this is our third step. So left step, left shift, then we check the degree. And if the degree is an 8th degree polynomial, then we just do an XOR, and then we get the answer. So that's summarized right here. The xtime function, this is what they call it in the AES specification, but it is, it times a polynomial by x. So this is what's happening here. We left shift the value being multiplied by x. Then we check to see if the degree is now 8. If it is, we XOR with 1, 0, 0, 0, 1, 1, 0, 1, 1. Okay. And so let me walk through an example of multiplication using xtime. I'm going to call this polynomial here f of x. And this is x to the 6th plus x to the 4th plus x cubed plus x squared. And we're going to multiply it by this polynomial, which is x to the 4th plus x cubed. We skip the x squared term plus x plus 1. Okay? So I'm going to write out the different parts. What we want to do is we want to figure out what f of x times 1 is. We want to figure out what f of x times x is. Then we want to figure out what f of x times x cubed is. I'm leaving out a step because we're going to have to do something with x squared, even though there's no x squared in this polynomial here. And x to the 4th. And so if I can multiply this polynomial by each of these terms and then add them together, and remember adding is just the same as an XOR, then I will have the answer I want. Well, f of x times 1 is easy. That's just the original function, our original polynomial, which is 0, 1, 0, 1, 1, 1, 0, 0. F of x times x is the same thing as xtime of f of x, which is we shift the polynomial 1 to the left. We check to see if it's overflowed, if the degree is 8, and it's not, so we don't have to do the XOR step. All right. To get to x cubed, we're going to temporarily go ahead and figure out what f of x times x squared is. And that will be xtime of this polynomial here. Multiplied by x squared is the same thing as taking the previous polynomial and multiplying by x. All right, so how do we do that? We shift it 1 to the left. And then we XOR with our usual polynomial. And the ones cancel. We're left with 0, 1, 1, 0, 1, 0, 1, 1. All right. We're not going to use that in our total because x squared is not part of this polynomial here. But we are going to go ahead and temporarily store that value because f of x times x cubed is x time of this polynomial, 0, 1, 1, 0, 1, 0, 1, 1. Well, the way we x time is we left shift these bits. And since we did not overflow, we do not have to do the XOR step. So then we get to f of x to the fourth. Well, that's just x time of what we had there, 1, 1, 0, 1, 0, 1, 1, 0. Well, that's 1, 1, 0, 1, 0, 1, 1, 0, 0. We're left shifting. That does overflow a byte. So then we XOR with our AES polynomial. And we get 1, 0, 1, 1, 0, 1, 1, 1. All right. So what we're doing is we're using xtime to build this list of powers, and then we want to add these 4 together. So again, I'm using XOR, 0 and 0 and 0 and 1 gives me a 1. 0 and 0 and 1 gives me a 0. 1, 0, 1, 1 gives me 1. 1, 1, 0, 0 gives me 0. 1, 1, 1, 1 gives me 0. 0, 1, 0, 1 gives me 0. 1, 0, 1, 0 gives me 0. And 0, 1, 1, 1 gives me 1. And so this is my answer. And I didn't have to do any really hard long division here. I'm using the xtime to build a list of the different things that we will add together, including an intermediate xtime that gave me f of x times x squared, which we could discard after we had used it to figure out f of x times x cubed. But the idea is that this may be faster and easier to code than this process over here is. Okay? Okay, I thank you for watching. See you next time.